cek cek cek. Oke, selamat pagi semua. Suara saya kedengeran jelas.
Selamat pagi, terdengar Bapak?
Oke. Nah, untuk hari ini kita ada kuliah tamu, tapi juga ada beberapa kelas yang presentasinya belum selesai. Kalau boleh tahu untuk kelas B, kurang berapa kelompok ya yang belum presentasi? Ada yang dari kelas B?
Maaf Pak, untuk kelas B perkiraan sekitar 3 atau sampai 4 kelompok gitu. Soalnya kemarin itu beberapa dari kita ada yang jadi panitia research day dan kita izin ke Pak Lutfi kan Pak. Nah terus habis itu disuruh presentasi minggu depan gitu. Jadi saya kurang paham juga sih, kurang berapa pastinya gitu.
Oke, jawaban. Nanti kita coba untuk kalian kalian tuh di kosan ya, Mas Yan berarti ya? Kita akan coba untuk presentasi setelah nanti eh, Dokter Parves ngasih kuliah. Kalau masih ada waktu, kita sempatkan untuk menyelesaikan presentasi. Tapi pesan dari Wiko kemarin juga, kalau memang hari ini kita tidak sempat karena terlalu mepet untuk ke lapangan, bisa membuat recording sih. Tapi untuk detailnya nanti kita lihat setelah nanti kuliah kamu ini. Oke, dan sedikit reminder aja untuk hari ini, untuk praktikum lapangannya yang bagian hari ini, mohon hadir 30 menit sebelum jadwal yang ada di oke, ada di itu ya, tabel itu ya. Jadi kita rencana akan berangkat 9.30 kalau nggak salah. Jadi mohon jam 9 sudah standby di kampus. Untuk presensi nanti kalau yang belum mungkin akan kami lakukan secara manual dari daftar yang ada di Zoom sih. Oh, hello.
Assalamu alaikum.
Waalaikumsalam. Hey,
How's it
Pak.
going?
Long time no see. I think it's
Yeah, it's been a while. It's been a
February,
while.
right? When you were here.
It was last year. When was it? Oh, was it? No, it was
No,
earlier
you
this
were
year.
here in February, I
February.
remember.
That's right. That's right. That's true. Have you seen the paper that we published?
No, not yet. Not
About
yet.
Donan. Oh, you should check it out. It's super fun.
Yeah. Okay, and you should share it with the students. But
Yeah, well, I mean, I've got a little bit about that today. So,
okay,
but I got
okay,
a bunch of other things. So,
okay. Cool, but I
How's
think
everything with you?
we already have like more than 100 people in the Zoom.
Cool.
So, yeah, we hope that you can give some offline lecture next time. But for
Yeah,
today,
yeah, yeah. That'd be cool. Well, the thing
mm,
is, I applied for some funding recently to come back to Indonesia.
okay.
And if I get that, then it'll be sometime within the first half of next year. So then we could do something in person,
Oh, oh,
inshallah.
I see. Yeah, yeah, yeah. And I think you already know that the dean of the School of Biology, Edinburgh, just visited us in November, last November.
Really?
Yeah, so
Cool. I
we
did
will
not
have
know.
more collaboration with the School of Biology as well as the School of
Amazing.
Engineering.
Fantastic. Very cool. I like it. So
Okay,
what's
but
the name of the Dean of Biology in Edinburgh? I can't even
oh my God,
remember.
that's a good question. I don't remember.
No worries. No worries.
But yeah, but anyway, I think I will start by just informally introducing Parfes
Sure.
to the students, and this is the biomaterial class for undergraduate that Pak Eko and Pak Bambang started maybe 5 years ago, if I remember correctly.
Nice. Cool.
And this year, me, Pak Torik, Pak Lutfi, were asked also to join the class, and we try to
Nice.
give some introduction about not just about the various biomaterial you can find uh, living among us especially in Indonesia. You can find a lot of biomaterial, but also just a little bit on the perspective from material science. So more on the mathematical modeling and also 3D scanning and how you can simulate those. And
Yeah.
today we have Dr. Parves Alam, which is, I think it's a long collaborator from the Faculty of Biology. I think we first met like what, 10 years ago?
More than that.
More than
You and
10 years?
I met like 2012 already.
Okay, yeah, it's been a long time. Been a long time. And I think I also share a little bit about the thing that I did during my visit to your lab still
Nice.
in Finland.
Yep.
And I think you have way more stories to tell the students today. But basically, right now, Dr. Parves is a staff. He is teaching at the University of Edinburgh at the School of Engineering. But his research goes way beyond the traditional engineering and more on the interface of also in biology. So yeah, without further ado, I think I'll just give the floor to Parves.
Cool. Thank you very much, Nuha. So I need to share my slides because it says sharing is not turned on. So I'm sending you a request and hopefully you can just give me permission to share.
Yep, should be okay now.
Okay. I think, are you able to see this?
Yeah, we can see it.
Excellent. I need to try and minimize stuff. So, oops, where is my stuff? Um, Let me just try and reshare that. I
Okay.
can't see myself at the moment.
Ah, and right now you are in Australia, right?
Australia. I'm in
Yeah.
Australia right now, doing some research on starfish.
Oh, wow.
Yeah, yeah.
You always
So,
find excuse to get away from the cold north.
oh, absolutely. You got to make sure that you leave when it's winter time, right?
Okay, yeah, yeah.
I mean, you spend time in Edinburgh, you know what it's like. I can't seem to see my own sharing screen, which is going to be a problem because that means I can't actually change. Let me just stop and start again. Sorry. Right. Open, share. Right. Hopefully you can see that.
Yeah, I can see it.
Cool. Now I need to get rid of this little thing on the side so I can see stuff as well. Okay, cool. So the way if you can see this, then we're good. Let me just, yes, okay. I think everything's working now. And if at any point you don't, you can no longer see stuff, right? Just let me know, because I'm going to be like changing the slides using these little buttons on the bottom left-hand corner. So I'll ask if the first slide does actually change, and then after that, I'm just going to assume that they all change perfectly well. Anyhow, as Nuha already mentioned, my background is material science, engineering. I'm currently, I did work in chemical engineering as well, but I'm currently in mechanical engineering at the University of Edinburgh. Um, and so I have like a fairly diverse background in the engineering sort of disciplines as well. My PhD was in structural mechanics, so sort of civil engineering. So I've gone through the whole transition of materials, civil, structural, chemical engineering, and mechanical engineering. So that's created and helped me sort of broaden my base in the engineering disciplines. But I've actually always been a closet zoologist, which is why I've been searching for like biologists and zoologists all around the world in order to further my knowledge and my experiences and expertise in the biological sciences. And now the way I've set up this talk and presentation today is to try and make things as easy as possible for everybody to understand, because obviously I can go very, very technical and very deep in the maths and the physics, and I don't think that's going to help anything or help anybody. It's going to be better if I can keep that to a surface level, and then you ask me questions if you need to go deeper. All right. So that's why I've called this specific talk, Short Stories in Science, where every page is a new experiment, because that allows me to, deliver this in the form of short stories, which I hope you will enjoy and be able to engage with. Now, I've just changed the slides. Can you see the slides changed? Nuha, do you see a new
Yes, yes.
slide that's,
Yeah, I
yeah?
saw composite
Okay,
changes.
great. So from now on, I'm just going to assume that the slides change and everything's good. All right. So as I mentioned, my background, a little bit about my background. I also have a PCIT from MIT in 2017, and I also have a docentur from Åbo Academy University. That's habilitation, which I got in 2013. My PhD, as I mentioned earlier, was University of Bath in structural mechanics, but that was in 2004. I've published two books. So if any of you guys ever do any work in composite materials with respect to biological structures, these books may be of use or of interest. I get no royalties from these books, by the way, so I'm just advertising them so that people, they're meant for undergraduates. So, I just want undergrads to use them and benefit from them. They're both published by the Institute of Physics, so hopefully you'll have. I don't know if UGM has a specific sort of read deal with Institute of Physics, but if you do, then you should have free access to these books anyway. Okay, so I can broadly sort of break my research down in, nowadays to two generic areas. One is the area of discovery, and one is the area of design. Now, the area of discovery will connect much more readily with a lot of you guys because you're biology background. Many of you are probably like part of KSK or KSE or some other groups where you're like working with large scale animals. Um, so, some of those stories hopefully will connect better with you. And I think the transition to design from some of those stories I'll try and make them as easy as possible. But in terms of design, I do work in mechanical metamaterials, composite materials, structural mechanics, structural materials, robotics, and other areas as well. So I'm going to start like with this little story. It's called A Web of Tales. Rumors, gossip, and serendipity. Okay. And Nuha probably knows what this story is about because he was at the very end point of this story during his time in Finland when he came over to Finland to work with me. So this story actually begins in Kenya. And I had heard these stories of like basically, I had heard a rumor that there was a group of mothers in Kenya that had started making garments and textiles using spider silk, right? And I thought to myself, but this is kind of impossible, right? Because spiders are cannibalistic. So if you put a bunch of spiders together, they just eat each other. And if you got one left, how much silk can you get out of that, right? Um, on top of that, scientists around the world, some of the top guys at Oxford University and everywhere, they've been trying this anyway for decades. Nobody's been successful. So how is it a group of mothers are managing to create these silks, enough silk to be able to, from spiders, and reel them to be able to make garments and textiles? So I basically jumped on a plane, got to Kenya, hooked up with a couple of friends there, and we decided to get in a car and drive around the whole of Kenya for several days chasing this rumor. So we went around, we started in Eldoret because I had different projects going on there, and we went all over the place just chasing rumor after rumor until we eventually made it to a place called Kisumu on day three, I think it was. And when we got to Kisumu, um, we met these guys. And so this is my team over there, right? So these are the guys in Kisumu who I met. When I got to Kisumu, I was just like, I found a silk factory and I thought this must be it, you know? So everything led to the silk factory, but it was actually just a Bombyx Mori silk factory. So this is your typical sort of silkworm cocoons that have been used for since 3,000 years back in China, right? Um, so unfortunately, the rumor wasn't true. There were no mothers who were reeling spider silks. They were reeling moth cocoon silks, which is has been done forever. Anyhow, I stand out like a light bulb in Kenya. Yeah. And I don't know if you know what the word Muzungu means, but these guys they came over and they were like, "Hey, Muzungu, what are you doing here?" So Muzungu it actually means white man, right? So they were just like, "Hey, white man, what are you doing here?" I was like, well," and I told them obviously after 3 days of searching, I was feeling pretty down, right? So I told them the whole sob story, and they said, "Oh, but we're insect farmers." And then I made the link. That is probably how the rumor began. You have these guys in this same village where there's this massive silk factory, and these are also insect farmers. So they took me over to their sort of insect farms, and they showed me they were they were rearing beetles and crickets and all sorts of different insects. And because I told them my story, they were like, "Well, we can do that stuff. I'm sure we can do that stuff, right?" So for the next 2.5 years, myself with these guys, we were bioprospecting for different kinds of spiders, right? And we were trying to find spiders that had special sort of egg cases or orb webs or any kinds of silks because they have different types of silks that they make. Um, any kind of webs that were particularly strong or that had particularly high deformation, that had really interesting properties that would potentially be different or world record breaking, right? And then we found this one guy here. His name is Nephelungus cluentata. And what I noticed when I grabbed the egg case of this spider species is that even if I made a hole and I put my fingers in the hole and I really tried super hard to open it up, yeah, it was almost impossible for me to tear open this silk egg case. And I'm fairly strong, right? And even though and this thing is really thin, and I could not open it. Yeah, so this one stood out to me. So I brought the biological material back to Finland, and I, asked Nuha to come over and do some work with it. So Nuha came over from Indonesia, spent, what was it, I think a month or something like that.
Yeah, more.
Was it 1 month? 2 months? I can't remember.
Oh, almost 2 months.
Almost 2 months, and he was in the labs working on these silks, and we were doing characterization, basic characterization, and mechanical testing. And what we eventually found was that the properties of this silk, in terms of toughness, were 193 megajoules per cubic meter, right? Which was about 60 megajoules per cubic meter higher than the previous record holder, which was an Italian cave spider called M. Menardi. And the fun thing here is that I presented this at MIT, and the guy who discovered the previous record was there in the audience, and he's from MIT. And I thought to myself, okay, we're going to have a bit of a battle, presumably, but it was not the case. He was very cool, and he was just like, "Hey, we need to work together. Let's do some stuff." So this worked out. This was it ended up being a very nice story, even though halfway through it was a bit of a sob story because the rumors were not true. Um, Now, one of the things that makes silks very strong, yeah, and this is now a little bit of technical information. One of the things that makes the silk strong is that when you're reeling, when the silk is being basically drawn by the spider itself, all of the molecules are sliding over each other. And as they slide over each other, certain regions that are like have high polyalanine content, right, on these proteins, because they have like lots of electrostatic forces of attraction available, they make contact with other polyalanine segments and they create these nanocrystals inside the threads. And because, the tubuliform silks, which is what we were studying from this spider, they have quite a lot of these nanocrystals, and they are known to have nanocrystals like that in quite large quantity. If you can check tubuliform silks or cylindriform silks, either of those are basically the same thing from different spiders. And you'll find that the nanocrystal content, as has been checked with Sachs wax or XRD or any of these other methods, is quite high, which is why these particular silks, have a very high toughness. Okay, now spider silks are not the only kinds of silks we've been studying. We've also been studying, I've had this PhD student, Atiq Rahman, at the University of Edinburgh, who's been working with me for 4 years now. He's an amazing student, and he's literally just a week ago submitted his PhD thesis. So, inshallah, he'll get through this through the Viva Voca, or the horrendous oral examination, as we otherwise call it, over here. But he's been looking at these moth cocoon silks, and these, funnily enough, are the exact same cocoons that I brought over from that silk factory in Kenya. Because obviously I was there. I thought to myself, well, why not just grab a bunch of cocoons while I'm over there, right? So I grabbed these cocoons, brought them over, and he's been doing research on those cocoons since. Now, a lot of people have been studying tensile properties of silk cocoons, and they've been cutting the cocoons and all sorts, right? So we wanted to look at it in a different perspective, because if you are a predator, yeah, and they have different types of predators, they'll have like mice and some birds and certain rodents as well, certain insects, they will try to gnaw through or pierce through the cocoon, right? But the cocoon at the end of the day is meant to be a protective structure for the babies. If you look at, anything to do with babies in nature, everything is about protecting the babies. And there's no difference here when it comes to egg cases of all kinds, right? So we started looking into the things like tear resistance and puncture resistance and stab resistance of cocoons, yeah, of complete cocoons. And the reason for that is, if you imagine a tension test would be something like this. You grab, I don't know if you can see me, but you grab your material and you're pulling like this. No animal is going to do that with a cocoon structure in nature. It's going to be like a complete waste of time because the tensile strength is way too strong. It's not an optimal way of tearing into something, right? What's going to happen if you have a tooth or a claw is you're going to puncture first and then you're going to try and tear something open. So those two mechanisms of failure have never been researched for cocoons. A multitude of people have researched tension, yeah, but very few people have looked into puncture, tear, and stab. And when I say stab, the reason we look into stab, that's with a knife, is because it's an analog or a homonym to a tooth. It's got one serrate, it's got one sharp edge, and it's got a slightly tapered structure. If you only use pins, that's fine. That's a little bit more potentially like a claw. But if you have like a knife, it's a little bit more like a tooth, right? Anyhow, what we found is that these Bombyx mori cocoons, in terms of tear energy, that they have, a perfect trade-off between tear energy, yeah, and density. So they're right there at the very bottom of this concave, which is a trade-off curve. You could call it a trade-off curve, yeah. Sorry, these are actually called convex trade-off curves. I used the wrong term there. And it's right at the cusp of the convex trade-off curve, which means it's kind of like sitting in a place where it's got good tear energy. At the same time, it's not either too high density, um, but it's not very low density either. Yeah, so it's like somewhere in the middle, which is very interesting because nature has these trade-offs when it comes to materials over and over again. And one of the reasons I think that exists is because, it could potentially, you could say, you could argue that it should have a lower density if it's to be a superior material, right? But biological materials are multifunctional, not single function. So a cocoon is not only trying to protect in terms of tear, stab, puncture, or tension, or anything like that. It's also gas permeability. Yeah, it's also moisture regulation. It's also thermoregulation. So when you're trying to like balance all of these different parameters together, you do need to like sometimes have a little bit of give. So yes, the density could be lower, yeah, similar, let's say, to polypropylene nonwovens, but maybe that would have a negative effect on thermoregulation, for example. So we need to consider these things as multifunctional materials. Interestingly enough, yeah, we also did a lot of research recently. I had a French researcher from École Polytechnique in Paris come and join, and I really love these raisin skates, because they're always smiling. You never see the smile because you're usually above them. But if you ever get the chance to see them smiling like that, then you're a lucky person, right? But they have these beautiful sort of horned egg cases as well. And these egg cases that they have are Bouligan structured egg cases. So they're like twisted plywood, right? And they also, very interestingly, have tear energies that are very similar. And we've done the tests, very similar to the Bombyx mori cocoons. So now my question is, for flexible egg cases in general, are they all very similar in terms of tear energy? Is that the maximum limit? I don't know. This is something that we need to look into in greater depth and detail as time goes by. This is our stab testing machine. So obviously, yeah, there's no stab testing machine that's been made for B. mori cocoons, right? So we had to make our own. So we made our own version using HOSDB standard knives, and we like had a full ingot, and everything's just like set up nice and simple. And we can parameterize this for different kinds of materials as well. And it did its job basically. If you look on the right hand side, you can see the fate of that cocoon at the bottom there. It's not looking good. Yeah. But what's interesting here is that the stab resistance is pretty decent when it comes to these cocoons. If you like imagine, you know, that knife being a tooth instead of a knife, there is a good degree of penetration resistance against that knife, right? And not only that, but it's like the structure of the cocoon deforms in such a way that it preserves its incompressibility for as long as it can, So incompressibility in solid mechanics means that you do not have a change in volume as a function of deformation. Okay? And you might be asking yourselves, well, what's the benefit of that? Well, if you can preserve the volume of the cocoon for as long as you can, then you potentially preserve the life of the animal inside because the animal will have a volume. If you keep reducing the volume as a function of penetration, at some point that animal's going to squish, right? So it deforms massively first, but it deforms massively in such a way that the volume of the cocoon is preserved for as long as it can until actual penetration and perforation, right? Um, Interestingly, if you take a needle and you puncture in the same way, yeah, you have exactly the same setup, volume is preserved, but you have a very different kind of curvature. So with a something similar to a tooth, the deformation is a sharp rate of decline. Um, and then the normalized area is declines quite sharply, and then it like tapers off. But with a needle, it just goes right the way through, and that is ultimately a failure mode mechanism issue in that the knife is constantly having to cut, which is similar to tooth, but a puncture needle, which is similar to certain wasps, they try to puncture cocoons, right? And they have a needle-like structure. So they actually, once they've punctured, it's kind of like a lot of slip and friction based failure, right? Hence, it's linear. We also did some work on these cocoons with this is one of my old students from a long time back, and we just tried to re-gum the cocoons. So we, thought to ourselves, well, these are really good materials at the end of the day, and they're made of fibroin and sericin, and sericin is basically like the sticky glue that holds these materials together, the fibroin, right? So what we did is we basically degummed these silks, flatten them because as a cocoon it's of no use, but flatten them, yeah, straighten them out, and then put the gum back in. And what we end up having is like a higher toughness material that's lower stiffness. But, again, it's a trade-off at the end of the day. But that's one way of using. So that's like bioutility, using a natural material to create an engineering material that's of benefit to us. And there's about 50 tons of Saracen waste, by the way, each year, um, that, you can account for if you just do this. So now I'll just move on to the next story. Um, and this one's called The Truth Hurts, Pink Unicorns, question mark, tree climbing fish, right? So if you speak to people about pink unicorns, nobody believes you, right? Well, it's the same situation with tree climbing fish. If you speak to people about tree climbing fish, nobody believes you because they're meant to swim. Now, pink unicorns actually do exist. Um, and there's proof behind this because a rhinoceros is actually, etymologically speaking, the name comes from a unicorn, right? It means unicorn, right? Um, and if you have an albino rhinoceros, and they do exist, then you have a pink unicorn, right? There you go. Well, equally, you have fish that climb trees, and we did a lot of work at UGM with those guys. And Pat Bambang, who I believe, with Pat Eco started this course, I think Noha mentioned that at the beginning. So he introduced me to these originally. He said, "Yeah, these fish with like they do crazy things." And so we kind of like went over to Semarang, where we like found these fish, and they're really cool. And I hope you can see this video. Check this video out on the left. This is the team on the right here, or part of the team. The team was actually bigger than this, but this is the team photo on that day. Yeah, but check this out. You have this fish jumping off a vertical surface, hopping across the water. Yeah, and then wait for it, jumping off the water back onto a vertical surface and holding on. This is a fish that can literally do anything. We don't have robots that can do this, you know? They can swim as well, by the way, because they're fish. They can burrow, they can dig, yeah, they can climb trees, they sunbathe, they do all sorts of stuff. They're terrestrial. They are very, very bionically capable. And this is like a nice video of it jumping across the water, as you can see here. And it does this by taxiing, yeah, but sometimes, yeah, so it has a couple of taxis and then it just shoots off the water surface, right? But sometimes it actually, when you skipping stones, if you grab a stone and you throw it across the water and it just bounces. So we've also seen it just bounce across the surface of the water. Now, the way in which it sticks is its own thing. I actually went to Australia like in 2019 to continue some research on this. So the ones we studied in Indonesia with my PhD student back then were Aditya Wicaksono, um, were like Periophthalmus variabilis. But in Australia, I came and was studying Periophthalmus gracilis. Latin names are not my thing, sorry. But, and this is really cool because this is the first time. Check this guy out as he goes. This is the first time. Okay, and that's me skateboarding as well. I can't even do a full. That's a like I can't do a full loop in the full pipe, but this fish can do a full loop. Look at this. So it's upside down. Check that out. Look from the top now. Unbelievable. Using the fruit and nuts box as well. Look at that. So you've got Stefan adhesion, you've got capillarity, you've got keep going. So now he's face down. He's face down. So he can handle face down as well. Look at that. Now there's a lot of stimulation here. Like that's amazing. Do you think? Absolutely amazing, right? So it can stick because it has very flexible fins. It's got like a lot of hyaluronic acid in the slime, which is a sticky sort of substance, which like induces a lot of hydrogen bonding, van der Waals attractions, and so forth. So it affixes through capillarity and Stefan adhesion, and that is basically how it can like climb trees, climb rocks, and so forth. There are other terrestrial fish that cannot climb in the same way that this one can, and that is because the fins are much more stiff. And even though they are secreting similar kinds of hyaluronic acids, they can't flex their fins enough to be able to stick to vertical surfaces. So that is the magic trick that the tree climber has that none of the other ones have. Here's a new story now. It's called Oh Get a Grip. Some lizard claws are more equal than others, drawing from George Orwell's like Animal Farm, right? So this work was done in Australia as well, which is where I am right now. Even though I'm doing starfish now, the last time I came here was to work on lizard claws. And what we did is we studied different types of claws from a shape perspective for the purpose of like designing novel robotic grippers, right? But we needed to first understand how biology worked because biology has optimized a lot. And we have arboreal lizards and we have was it like burrowing lizards. And if you look at the different styles of claws, they have different shapes. The arboreal lizard has a much tighter curvature. Yeah. It's got a much thicker sort of central section. It's like it looks like it's meant for gripping onto trees, whereas the burrowing claws, they look like much longer, spoon-like kinds of claws. And what we actually found is that, the arboreal lizards, they have, very idealized claws for gripping onto trees and surfaces. And we did this using a variety of different sort of test setups. I won't go into too much detail, but basically the V varius, which is the arboreal one that we studied, like trumped every single other lizard that we looked into. Now, what's interesting is we thought we could go better. So we took the V-Various claw, right? And we like, as engineers, we have like parametric design methods that we use to, design what we consider the ideal structures. So we parametrically designed from the V-Various claw, the arboreal lizard's claw, in two different directions. So we'd have like a full test setup with 20 different types of claws. Some of them are more shallow, some of them have higher curvature, some of them, et cetera, et cetera. What we found was that in every test, no matter how much, if you looked at every single claw that we had parametrically designed, the lizard claw was still the best one, regardless, in terms of its gripping strength and gripping efficiency and its consistency in gripping. And that is like quite unbelievable in some ways, right? What's going on here? So I guess in some ways we need to look at more arboreal lizards. Yeah. Do they all have highly optimized claws for climbing? And maybe there are some that climb more, some that climb less. We need to look into this because there may be some transitional sort of understanding that we can apply to things like robotics as well. And I've been doing like, taking this work further to Rice University in Texas and to Costa Rica, where I've been doing work with these kinds of lizards and their claws. And this time, this is recent research that we've been doing like last year and the year before. And also to Costa Rica, as I mentioned, where we've been trying. So this story is a new perspective on open gun laws here. So I did a lot of research there on 15 different species of lizard. Yeah. And that's kind of where I'm going to end that story. But what we have found from that work is that we found certain robotic manipulators that we can design and apply the claws as end effectors, and it's the arboreal lizard claws that are coming out on top again. Out of all of the ones we have, 15 different species then from America and Costa Rica. So since I'm speaking about Texas and I was there, and it was pretty cool actually because everybody's walking around with guns, but everybody's also really friendly, and there's no police anywhere because you don't need them because everybody's got guns, right? So it's kind of like awesome. Anyhow, these are tales of the gun-toting pistol shrimp, also known as a snapping shrimp. This is some work that we did in Indonesia, and I can't remember when. It was a while back. This involved quite a few students from Universitas Gadjah Mada, and what we found with this guy is that it is a thermomechanically optimized structure because this gun, it has a gun on one arm, and it's just like shooting with this arm, bang, bang, bang. And if you're applying that much pressure, you need mechanical resistance, but you also are probably, because of the pressure, generating a decent amount of heat. So how come that heat isn't damaging, the plunger system or the socket system? How come it's not reaching a level where that heat is potentially even like causing problems to the flesh underneath? Well, if you look at the structure, it's a 50% porous structure on the inside. It's a porous, Bouligan type structure, chitin as well. And that acts, we believe, as an insulator. We did some simulations to prove this. And, the outer and inner sort of layers of this plunger are actually hard calcified material. So there's your mechanical sort of benefit. So that you have in the snapping shrimp a thermomechanically damage tolerant structure, which we have now been looking into developing new materials from. And this is PK. He is hopefully submitting his thesis this month. He has to actually because his oral examination is in March. So I'm pushing him like crazy at the moment and going through his thesis at the moment. But he's been looking into creating porous Bouligan structured materials using SLA printing, 3D printing techniques. And what we are finding is that these materials that we've been subjecting them to impact, to bending, tension, shear, stab, and all sorts of different kinds of mechanical loading conditions. And what we're finding is that there are certain levels of porosity within the structure that you can like optimize for in order to gain the maximum benefit of of a porous Boudigan structured composite. And this is something that hasn't really been studied at all. Okay, so this is a new story called The Karate Plank Breaker's True Nightmare. And this is about damage tolerance in dragonfly wings. This is some work that I did with City Fausia quite early in my days at UGM. I would say like maybe 2013, 14, something like that, right? Some work we did with Pak Bambang and Pak Hidayat Sosil Wahidi as well, who has unfortunately, from what I've understood, passed away. Um, but yeah, this was really interesting work because the dragonfly wing, if you think it's flapping at tens of times per second, right? So 30 to 60 hertz, right? And it's super thin. So why doesn't it break? That's the question that I had on my mind. Why aren't these breaking? And it's not even the fastest flapper. The fastest flapper is like the Scottish midge, which flaps at more than 1,000 times per second, right? So flapping rate seems to be correlated to some extent with the size of the animal. Point of interest and point of note. Anyhow, these dragonfly wings, they actually have lots of soft resilin or rubbery pads in between all of their joints. And that's something that like dissipates mechanical energy during flapping, which allows the preservation and conservation of the structure of the wing while it's flapping. And that is ultimately the answer to that question. I don't want to spend too much time on this, but we applied that concept to timber trusses. So these are massive, which indicates scalability, by the way, because the dragonfly wing is tiny, timber trusses are massive. And what we did is we put like really soft glue around the bolt, just 2 millimeters or 2.5 millimeter thick glue layer, really soft rubbery glue layer around these bolts. And we more than doubled the fatigue lifetime of timber trusses by mimicking the structures of these wings. Okay, now this is a new story. It's a moment of realization, which is that I know nothing about dinosaurs. That was something that came to my mind around 2013. And I was just like, I don't know enough about dinosaurs. It's driving me crazy now. And while I'm, giving you this information, I think there is a great injustice that we have in this world right now because dinosaurs, they melted into oil, didn't they? And nowadays, we take that oil and we fractionate the oil to make plastic. And we use the plastic to make plastic dinosaurs. I don't think that's respectful, you know? Or is it? Maybe it's just a perspective issue, right? Anyhow, so what I did is I decided to go to the University of Cape Town. I called up Anusia Chinsami Turan, who is one of the world's top dinosaur experts or paleontologists out there. And I just said, look, I want to learn about dinosaurs. Can I come over and just learn directly under you? She was like, sure, come over, you know. So I went to Cape Town for 2 sabbaticals and it was fantastic. And, she told me to learn about whales. And, because they are the largest creatures that we have right now. And so we can draw a lot of parallels from whale structures to dinosaur structures. So what I did is I studied sperm whales and baleen whales. And what you notice is that there is certain traits in whale bones that have mechanically optimized, you could say. One thing is aperiodicity, right? So what we have found in recent times is that aperiodicity actually increases the fracture damage tolerance of a structure. You see? So this is really interesting to me because it's like if you look at bones in general and most natural structures are aperiodic, which means that they have a natural fracture damage tolerance. There are only a few that you find that are not aperiodic, like honeycombs and that kind of stuff, right? But most others are. So it seems that now you could say, oh, it's kind of randomized, therefore it's aperiodic. But you can't necessarily say that because there are a lot of things that are very refined in terms of structure. You just look at muscle fibers, very refined structures, spider silk fibers, very refined structures, honeycomb structures, very refined. So, nature is able to create good, like primitive human understanding, like in terms of symmetry, geometries, but it tends towards aperiodicity. And, I think this is a way of preserving the structure under high stresses, high pressures, and so forth, right? Another thing that it has, if you look carefully, is porosity. And pore shapes and sizes change from area to area in different types of bone. And this is true in, all of the whale bones that we've looked at so far. So that's interesting because I released this work in 2011, And I came up with this equation, which basically says, I'm not going to go into detail in this equation, but it basically says that the important thing in terms of structure preservation with any material that has porosity is the width, yeah, relative to the loading direction and relative to the total width of the structure that's being loaded. So you'll find with a lot of natural structures, yeah, that they have oriented widths and oriented pores. And you can see, for example, in the baleen whale very clearly, high aspect ratio pores, then you have low aspect ratio pores, and they have a very specific orientation. You could say along the axis of the of the animal, right? And this is interesting to me because as engineers, we try to design structures based on this kind of porosity, right? We try to orient pores in order to make structures work the way we want them to work and to refine the properties. One example is in these sort of three-dimensional porous systems where, Fleisch et al., they basically parametrically optimize the pores in order to optimize the structure of metamaterials, right? And you can have like pore structures like peanut shaped pore structures that are used again to optimize the properties of metastructures. And then one of these is like my favorites. You can structure the pores in such a way to achieve zero Poisson's ratio, which means that when you stretch these materials, that normally when you stretch a material, it'll squeeze inwards on the side, right? So if you imagine stretching rubber, it'll become thinner, right? But if you stretch this material, because they've organized the pores in this very specific way and with a specific structure, when you stretch it, the sides stay in exactly the same place. Now, there are actually materials known as auxetic materials, which also exist in nature, that if you stretch them, they become fatter. And one example is beneficial, I think, to pregnant women because it's the skin of human skin, salamander skin, etc. That if you stretch that skin, it becomes thicker. It doesn't become thinner. Of course, it reaches a point where it can't become any thicker, and at that point, you start getting stretch lines, and you'll see that on pregnant women. If the belly stretches beyond a certain point, you get the stretch lines. That's where you get failure. But up until that point, the skin is just becoming thicker and thus improving its load resistance capabilities, which is very cool and very clever. And we see that ubiquitously throughout nature. Another thing that we might notice in these bones is that we have minimal surface-like structures. So I don't want to go too much into the mathematics here, but if I pull up this image from this one, you can see that it's like an hourglass. So it becomes thinner in the center and wider at the top and the bottom where it's connected to the main sort of members that go crosswise. So what that's doing is it's improving stress transfer, right? And a minimal surface mathematically is defined as where the curvature is equal to zero. So the first differential by the second differential to the power of 2, 3 is equal to zero across the curvature, right? Now in materials, we say the minimal surface is basically like the hourglass. So you're approaching that kind of zero type curvature as you come close to the center, right? And we actually make metamaterials based on minimal surfaces in order to reduce stress concentrations within material structures. But what I find curious and amazing is the fact that nature has been doing this for absolutely eons already, right? So again, we're far behind. We're always far behind. Last thing I want to tell you about these structures are that they functionally graded, right? Which means if you look at the baleen whale, you can see there are clear layers where you have different, shapes of pores and so forth. Why is it layered like that? Well, we actually do this in engineering design as well, except we do it in a much more simplistic fashion. If you look here, for example, you've got like basic trusses that are cross trusses, but they're hierarchical and they're thinner at the top and thicker at the bottom, and they increase in thickness as you go from top to bottom, right? So what this allows you to have is a strain stiffening and softening, stiffening, softening reaction to load bearing, which could have benefits when it comes to crash resistance and that kind of stuff, right? We do this also with chiral structures, but I don't want to go too much into detail there. But we do that with chiral and more technical structures as well. But even though we do that, our structures are still not as technical as the ones that exist in biology. There is so much mathematics and physics that we need to go deeper into when it comes to biological structures to truly understand how they work, if we're to gain good insights for engineering. And even if we do that, if I'm completely honest, our manufacturing capabilities are what limit us from being able to replicate the complexity that we see in biology. But we can still gain some benefit by simplified abstraction mechanisms, right? And that's how we approach biomimetic design and bio-inspired engineering, because that is the only way we can do it, right? Anyhow, now that I gave you that speech, here's us attempting to think outside the box, right? Because I'm thinking to myself, biology is always winning, right? It's always got the stuff before us. So how can we think outside the box? How can we do new things, right? So 2018, I had this idea of like taking fourth geometrical structures and projecting them into three-dimensional shadows of themselves, right? And these are called four polytopes. You've got lots of different variations of those. The most famous one is the hypercube or the tesseract, yeah. So I got this really good student in on a PhD to do the work on this, and it was revealing, I can tell you that much. So to explain what this means, if you look at here, you've got a square, right? And you've got a cube and you've got a hypercube. Except that you don't. You've got only a square and you've got a shadow of a cube, because actually that cube that you see are lines that represent the projection of a cube on a two-dimensional surface, right? And then you've got a shadow of a tesseract or a hypercube. So you've taken the fourth geometrical structures with the Schlegel perspective, you've taken it down to three-dimensional geometries, and then you've taken it from 3 dimensions to two-dimensional flat surface and represented it on a flat surface with just lines. Okay, so we take it to the third dimension because then we can make three-dimensional structures and 3D print them and stuff. And what we found is that actually our structures like tesseracts, orthoplexes, pentatopes, and so forth, that they seriously outperform a lot of other conventional engineering structures that already exist. Yeah. In terms of specific stiffness, specific strength, and shear, especially in shear. I mean, we are so far ahead of honeycombs out of plane in shear, right? And gyroid structures, which are like the ones that were hailed as being the best of the best because they're like, minimal surface, right? They're far exceeding all of those. So here's us trying to think outside the box and trying to, find ways that, nature hasn't covered already. However, what we realized is that this ultimately boils down to what is known as structural hierarchy. And sadly for us, structural hierarchy already exists in nature. You can look at wood, you can look at bone, you can look at a lot of natural structures, and they already have structural hierarchy. So, okay, unfortunately, the concept already exists in nature, so we didn't entirely win that battle. No worries. Let's try again. So this is another one of my students who's also graduated now. And these are like teeny arms. They make everything function well. Look at this as a new metamaterial where, can you see those arms? They're twisting and then they're interlocking. So what we did here is we basically got these little circular structures. We got these flowers. We made these flowers, right? Because what happened was Li Ying, she came into my office, wanted to do this thesis with me. And I was like, well, what do you like? She was like, I like flowers. I was like, okay, let's make metamaterials out of flowers then. So these are the flowers, the big flowers. And at the bottom, we have these little circles with small arms with different sizes. And by controlling the sizes of the arms, you can control the rotational capability of those arms, right? And by doing that, we end up with strain stiffening, softening, stiffening, softening, stiffening, softening, which again has implications for like impact resistance, crash resistance, elastic recovery, and all these kinds of things, right? But ultimately, this is a geometry guided concept, right? And geometry guided concepts exist ubiquitously throughout nature. So even though we're trying to think outside the box, if you look even at that tree climbing fish again, and here's Adit in person. Uh, basically, what we found that there's a piston. It's a geometrical piston that like antagonistically allows the pelvic and the pectoral fins to move uh, independently, right? So you have one moving, oh, sorry, antagonistically, yeah? So as the piston moves in and out, it basically pushes and aids the movement of the pectoral versus the pelvic fins. So geometrical guidance exists in nature. And so we lost that battle as well, unfortunately. But no worries. We try again, right? Now we have geared metastructures, right? They're fixed geared metastructures. And this is one of my students called Anne, who's currently on her PhD. And they basically interconnect. They're discontinuous structures. So they like have a property until they connect, and then you have a new property. So you have strain stiffening, softening, stiffening effects. Now, these are basically geared, they're discontinuous, and they're interlocking. That's what the functionality comes down to. And unfortunately for us, in nature, you already have gears in the leaf hopper, right? So these are ancient gears, like long before gears were even created by humans. The leaf hopper had gears in its legs. And starfish, which is what we're researching here, are discontinuous metastructures that strain stiffen as a function of motion. So we failed. We didn't fail. We had cool stuff. We made new research, right? We made new stuff, but we couldn't again surpass biology because biology had thought of the concept already, right? So now um, I'm going to introduce you to my current obsession, which is necro robots or necrobots, right? So necrobots, they're cool because if you can't we need to be sustainable. This is a sustainable world, right? We want it to be environmentally friendly. We want to do all those things that are good for the world, right? So necrobots is the way to go. And why am I saying that? Because conventional robots, they're like made of metals, they're made of plastic. So these are all materials that are not necessarily great for the environment, right? There's a lot of processing involved. There's a lot of mining involved. There's fractionation involved. There's like end of life. There's so many levels to which these materials that we use for robots right now are not good for the environment. So necrobots, they're made of dead bodies of animals, right? So if you can't beat them, conjoin them. And we've done a whole bunch of projects with necrobots now. One of the early ones that we did was this is one of my students, Jordan, and this is a five-horn rhinoceros beetle. And what we did is we like basically put this mechatronic system inside the body of this beetle to get it walking. And check this out. There you go. Here it's walking, and it's carrying a load of 500 grams, right? And that is 6,500, that is a payload ratio of 6,500% approximately, right? So that's where if you look at all the robots created through history that have had the highest payload ratios, right? And look at the names on this. This is like we've got the Michael Jordans of the robot world here. You've got Superbot, Miniwegs, you've got Antbot, Minitor, Unitree. These are like massive names in the world of robots. We called our robot Poka, right? Which means insect in Bengali. Um, and our payload, Pocket has a payload ratio that is far higher than any of the previous robots that have been walking on the face of this planet. And a lot of that comes down to the fact that the natural structures of the beetles are highly optimized for low weight but high strength and high stiffness. They're composite materials, they're laminated materials, and they're porous materials as well. So these beetles have these optimal bending resistant structures, and we made use of that in order to be able to create these miniature Necker robots with massive payload ratios. And you think about the difference. The previous record holder for payload ratio was 531%. Our Necrobot Poca, 6,500%. The difference is massive. So it clearly shows that there is a lot of potential in terms of like load-bearing capacity for Necro robots, right? Now, this is a recent one we did at Gajah Mada University. And this one I finished up in February, wasn't it? And we've published this already with Pat Donan in Advanced Robotics Research. And it's the world's first endoskeleton walking robot. And here's a video of it moving and starting to walk. And this is a lot of work actually went into this. And here, this video at the bottom is even cooler because like it's meeting the original, the OG, and they're becoming BFFs. This is like you can't get better than this situation, right? So yeah, I mean, there's a lot of work involved in this, but what we were trying to do essentially was mimic the sprawling gait because these varionicluses, they have a sprawling gait, and we did that quite well. The majority of our metrics showed that we mimicked the sprawling gait with a very simplistic mechatronic system that we applied to the legs and to the spine. And a lot of things went wrong, but a lot of things went right, and eventually we got it working. Now, one of the issues with necrorobotics is that no two skeletons are the same size, right? So we need to have actuation mechanisms to enable one size fits all, right? And these guys I lovingly refer to as the necroboids, right? Uh, and what they did is they looked at dog skulls and the actuation mechanism for dog skulls, and they try to create a mechanism that fits a multitude of different sizes. So if we create the actuation mechanisms, the contact points, the jointings in such a way that we can apply it to any skeletal structure for the same animal or for a different animal, maybe even, yeah, that allows different sized structures to be just applied, then there is long-term longevity and durability for the idea of necrobotics. If you have to redesign for every single new skeleton, we have a big problem, right? Because that is not feasible. Okay, so in terms of mass production, this is the way to go. And we found like this simple structure here on the bottom left that you can see works for a very large range of dog skulls. And necrobots are renewable, sustainable, they're biodegradable, nature friendly. They are preformed structures, skeletons are and they're field tested by the animal. So we don't even need to test them, right? They're available as bio-waste. Food waste industry has so much going. Yeah. So there's a lot out there. Insects have short lifespans. They mate, they eat, they die. That's it. A lot of them live for a few days max, right? So they have short lifespans. So just we could collect if we're farming insects, let them mate, do their thing, they're happy, they die, and then you got lots and lots of dead bodies everywhere. They're also low energy and low pollution, right? So there's a lot going on. And necrobots, I think, is the future for the democratization of robotics, because like the high-end robots are only preserved for industry, for like the bigwigs out there, right? The billionaires. But like necrobots are available to everybody. You 3D print components, structures, joints, make them available to everybody, right? It's the same with the e-waste based robots. The democratization of robotics is there, it's available. That's what we're trying to do. We're trying to make sure that everybody has access to their own robots. And at the end of the day, if you don't have any friends like me, then you can make your own. And
Okay.
that is the end of this talk. I hope you enjoyed it. I'm sorry I went a little bit over time.
No worries. Thanks, Parvez. I think so. So basically, to put it in context, after this, we will have a field trip with the students. And
Nice.
hopefully, from listening to the lecture from Barfest today, you have a different perspective when you go in the field, right? So I think as a biologist, we always look at the diversity, evolution, but also when we start thinking it in a material science perspective, you can put it into numbers about, nature has their own design for engineering, and maybe it is useful for something. So yeah, I hope you can try to apply this different perspective from. I think this is mostly second year student, so you
Nice.
have a
Nice.
long way to
So they
go.
got time to think. They got time to
Yeah, yeah,
think
yeah,
and do fun things.
yeah.
Excellent.
And I think that's what I personally learned from you. So putting numbers
Nice.
into what I see in nature. And
Awesome.
yeah, and actually I use the regenerated silk. I think you said the Jijang one, right? Yeah, I use it for
Yep.
the midterm for the students.
Yeah.
Well, I hope you guys enjoy the exam.
Oh,
But
are you regenerating silk with E. coli, like as a
no, no,
symbiote?
no, no, these just like a case study to learn more about the basic. Yeah, but
Nice,
hopefully
nice.
we can try to play around with that.
Should.
But yeah, I think I should give the time for the students to ask questions. And yeah, there are some comments on the chat, I guess. Okay. But yeah, if you have any question, please you can just open your mic, or you can also type it in the chats.
I like this man-made horrors comment here.
Yeah, yeah.
Excellent.
Okay, but something that I've been thinking for the next year practical, because this year we try to do some 3D scanning of, big materials and try to do
Nice.
some modeling out of it. I think
Yeah.
some works, some doesn't work. So
Yeah.
yeah, we can have your inputs on what kind of
Cool.
practical.
Cool.
And definitely next year we will try 3D printing.
Yeah. I mean, one thing you guys could do if you have you got a 3D scanner, like a blue light scanner over there?
Right now, I need to check with Pak Donan, but it is something that Pak Lutfi and Pak Bambang wants to get. I mean,
Nice,
we
nice.
have whole bones collection in the museum,
Yeah,
but
yeah,
for the cards, we just use our phones using
yeah.
Android scan. But like,
Nice.
okay. Cool. So anybody wants to ask anything to Parfest?
I mean, when you have the tool, if I'm over, um, if you do some stuff with like, for example, you know, like full bodies of animals, I could show you how to do, for example, just take the direct output from that and do CFD simulations to see like
Oh,
airflow
yep. Yeah.
or like liquid flow. So it could be a fish or it could be a crab or it could be, and you could just get some perspective on the hydrodynamics or aerodynamics. It's quite a simple thing to do, which is, why
Yeah,
it can
yeah,
be
yeah.
taught quite easily. Yeah.
Yeah, especially, I mean, we have a lot of insects collections, even
Yeah.
some, some big animals as well. Um,
Yeah.
but yeah, but I think because we need to prepare for the field trip, I guess.
Cool.
Uh, Next time when Bartos is here, I will let all of you know so you can have a chat with him and just ask any questions, or you can, ask him to go to a field trip with you. I think he's
That'd
one
be
who
fun.
always say yes to an adventure.
Yeah.
But
Absolutely. Absolutely.
yeah, but
Awesome.
anyway, I think we will still keep in touch with you, especially with the Edinburgh University. There will be more
Nice.
opportunities for collaboration. So
Cool.
always
Fantastic.
happy to have you here at
Sounds
UKM.
good. Sounds good. Welcome to the cold north. I'll see you guys
Yeah,
hopefully next year.
yeah, and
That's
enjoy the
that's the
summer
plan. That's
in
the plan.
Australia.
Right. Take
Okay,
care. See you
thank you.
later. Bye.
Yeah. Oke, itu tadi kuliah dari Parves. Rekamannya akan saya share di grup bagi yang belum sempat, dan karena sudah mendekati waktu field trip, sampai jumpa segera di Jatabi ya bagi yang field trip hari ini. Ya, selamat pagi. Dan kemudian untuk teman-teman yang belum selesai presentasi, mungkin akan kami arahkan untuk membuat rekaman, tapi akan kami informasikan lagi. Mungkin itu untuk hari ini. Terima kasih banyak sudah hadir di kuliah online dengan Dr. Parves. Semoga menginspirasi dan bisa kalian coba apply perspektifnya ketika field trip nanti. Oke, selamat pagi dan sampai jumpa.